Hello everybody, welcome to our video of our final project for ECE 3710 here at Utah State University. My name is Brandon Eldredge. I'm junior here at Utah State University.
I'm Trey Crowther, I'm also junior at Utah State University.
And I'm Tyler Rose, same. Our project intro is going to be the automated blind system. We found this system would be able to be beneficial for being able to automatically move your blinds up and down without having to pull the strings all the time. And we were able to accomplish this using stepper motors, whether they're moving in the same direction or opposite directions, to control the left and right sides of our blind system.
So how we wanted to control the blinds was by using a video game Wii nunchuck controller. This controller uses I2C communication protocol. We also have the goal to control the blinds with a microphone to be able to implement a type of clap on, clap off to raise them or lower them. So with the I2C, with the nunchuck is our first attempt to control the system. As you can see behind me, this kind of goes over an overview of this nunchuck specific I2C protocols. With I2C, you need to first send a start bit, followed by the bytes of information you want to transmit, followed by you receive and acknowledge or not acknowledge, and then finally a stop bit. So first, what we did with the nunchuck is it first needs the start bit, then you need to send the slave address of the nunchuck. For a nunchuck, it's 0x or hex A4. The nunchuck will send an acknowledge, and then the master needs to send the signal 40, wait for an acknowledge, and then 0. This just kind of initializes and gets the nunchuck ready to transmit data. To request data, you then have to send the start, the slave address for the nunchuck, again A4, acknowledge, send a 0, acknowledge, and then stop. So that is what you need to do to initialize the command, and to initialize the nunchuck to be able to read its data. Then to read the command, the slave nunchuck has a different address for reading data. So you send start A5, wait for the acknowledge. After this, the nunchuck acknowledges that command. It will then start to transmit bytes of data. It stores 6 bytes of data with the different motions. All we wanted to use was the x-axis and y-axis, which was byte number 1, and then byte number 2, and then we could stop. After that, we would be done receiving the data from the nunchuck. Once we got the data, the last step was to decode that data. You had to exclusive OR the received data with hex 17, and then add hex 17 to get the actual data that was coming out of the nunchuck.
Perfect. And then we also wanted the nunchuck to run on a 100 kilohertz clock. The system clock runs at 4 megahertz, so the math to manipulate that in order so it will run at the correct timing is you take the system clock and you find the period of it, which is 0.25 times 10 to the negative 6 seconds, and then for 100 kilohertz, it's 10 times 10 to the negative 6. And so the way that you manipulate this is by using the SCLH and the SCLL, which manipulate how long the frequency is high and how long it is low to give a total period. So the total period is SCLH plus 1 times the system clock, which is 0.25 times 10 to the negative 6, and then SCLL plus 1 times the system clock. And that will give us the entirety. So we chose 24.1, or 24 plus 1, which gives it a total of 20, and then, or plus 14 plus 1, which gives a total of 40. And then 40 times 0.25 times 10 to the negative 6 gives a 10 times 10 to the negative 6, which is a 100 kilohertz clock.
Perfect.
And we spent about 10 plus hours trying to implement this I2C with the nunchuck, but we're unable to get the communication to acknowledge. And because of this, we were unable to have time to also implement the microphone on the board, which also communicates with an I2C function. We believe this would be mostly due to some issues with the timing, with not being able to get 100 kilohertz, which we expected, and we will be able to learn from that.
Perfect. So instead of operating the system with the nunchuck, we turned to an alternative design by using the joystick interrupts on our STM32L476 microcontroller. The joystick is configured to pins on the GPIO pins on the board, specifically pins PA through P3, PA3, and PA5, and those can be connected to the interrupts the external peripheral interrupts, EXTI 0 through 3 and the 9 through 5 interrupt.
Yeah, exactly. So we use those interrupts to control the direction of the blinds, if they moved up, down, left, right. And then for the LCD display, we displayed the percentage of where the blinds were at, just the kind of the current status of where they were at. So we calculated that it takes about 3 full rotations of the motor to get from the bottom to the top. So we kept kind of track of a counter of how many rotations of the stators were used, and then kept track of the total percentage of how many times it would take the stators to rotate to make it to the top. So we just used that as a total percentage and then divided that and displayed that on the board.
And then for interrupt handlers in our functions, we had the left one put the left all the way up, left side of the blinds all the way up. The right button would put the right side of the blinds all the way up as you held them. Same with up, would put all up, and down would put both down. Whereas our center function was an equalize function where you just press it once, and then it would have the left side and the right side meet in the middle, depending on which one was higher or lower. They meet in the middle each time.
Exactly. So by using those 5 interrupts, we were able to control all of the blinds by going up, down. We will now go to the demonstration where we will actually show you the full functioning implementation that we designed. All right, so here we have the automatic blind system. We have just the blinds here connected with the strings connected to these extender cylinders that are rotated by the outer stepper motors. Both stepper motors are connected to 5-volt drivers that you can see in the back. Everything is breadboarded and connected in the back to the microcontroller. On the front, you see the LCD display. This is showing the status of the blinds. We have the left for the left-hand side and the number, and the right for the right-hand side. The number signifies the percentage that the blind is pulled up. So 99 would be full pull up. 0, obviously, as you can see, is all the way down.
All right, and then to show exactly what it can do, so we can go up on both sides, and then they count, go up together, and then as you can see on the LCD screen, the numbers are increasing together. They can go all the way up, so let's go up to halfway, right there, and then they can go all the way back down, bring it back down. There we go, all the way back down to the bottom, and then you can raise one side. So raising the right side, bring it up a little bit. See, bring it up about 20% right there, and then you can bring up the left side. It's 20%. Right there, and then you can, we separate them a little bit, give them a little distance between the two. Let's raise up the right side to about 60 here. So as you can see, one side, the right side is at 60% and the left side is at 20, and then we can hit the center button and then they will balance out and equalize. And then they meet in the middle. There's our functioning system.